السلام عليكم ورحمة الله وبركاته. أسعد الله صباحكم جميعا وكل عام وأنتم بخير. اليوم أول محاضرة في رمضان. هنكمل إن شاء الله معاكم بالهيت ترانسفير. وصلنا لهذا السلايد، حكينا عن الكوندكشن، حكينا عن قانونه اللي هو كان قانون فوريز لو، وشفنا أهم البارامترز اللي تأثر على الكيو كوندكشن، وحكينا كمان عن الكونفكشن، وشفنا قانون نيوتنز لو، شفنا أهم البارامتر اللي بتأثر على الكيو. and now we reach up to radiation. فرايحين نحكي شوي عن تعريف الراديشن وبعدين بنشوف معادلات. So radiation is defined as the energy, so all of them energy, and depends on temperature mainly. Okay? Energy emitted by matter in the form of electromagnetic waves or photons. Okay? As a result of a change in the electronic configuration of atoms or molecules. So those electrons emit certain signal, we call it waves, or we call it photons. Okay, and this emit thermal energy. Okay. Unlike conduction and convection, the transfer of heat by radiation does not require the presence of an intervening medium. So no need for medium. If we have no medium, then the radiation percentage will be 100%. If we have medium, then we'll have certain attenuation. In fact, heat transfer by radiation is the fastest mode at the speed of light, and it suffers no attenuation in vacuum. Okay, so if there is no medium, there is no attenuation, 100%. If there is medium, then there is certain attenuation. This is how the energy of the sun reaches the Earth. In heat transfer studies, we are interested in thermal radiation, okay, which is the form of radiation emitted by bodies because of their temperature. وحكينا متى بيكون في radiation from all bodies, okay, at the temperature above absolute zero, emit the thermal radiation. So above 0 Kelvin, we'll expect that anybody will have radiation or will emit radiation. So here it is, Q dot this emitted, okay, this is emitted radiation, and this is the maximum scenario. Okay, this is same equation but not for maximum, for general scenario. So this equation is general, okay, and this equation represents the radiation emitted by real surfaces. So what do we have here? We have epsilon multiplied by, so this is epsilon multiplied by sigma multiplied by surface area multiplied by temperature of the surface to the power 4. So if I substitute epsilon with 1, then we'll go back to this equation, which is the maximum scenario. Okay, and we call this scenario Stephen-Boltzmann law. And this sigma represents the Stephen-Boltzmann constant. Okay, so this is sigma, and its value, you should remember it, 5.67 multiplied by 10 to the minus 8 watt per meter squared Kelvin. And here we have very important notice that the unit of temperature is Kelvin. Okay, so when we'll substitute sigma with 1, if we have, so we can substitute 1, here it is 1, and this is now maximum when we have a black body. So black body represents the idealized surface, perfect surface, that emits the radiation at the maximum rate. Okay, So the maximum rate happens with the black body, and its epsilon is equal to 1. So this epsilon we call it emissivity, which is a measure of how closely a surface approximates a black body, for which sigma equal to 1, or sorry, epsilon equal to 1 of the surface. So this epsilon ranges between 1 and 0. Here in this table, we'll see the emissivities of some materials. So here is the minimum, far away from black body, and here we have, for example, this one. This is very close to ideal surface, black body, black paint. Okay, and other bodies. So here, if we have a black body and if the T surface is 400, so we can calculate Q emitted with respect to surface area by multiplying sigma, which is 5.167 multiplied by 10 to the minus 8, multiplied by surface temperature, and this surface temperature must be in Kelvin. So black body radiation represents the maximum amount of radiation that can be emitted from a surface at a specified temperature. Another direction of radiation that the absorptivity, the body or the rigid body absorb radiation. So absorptivity, which is alpha now, the fraction of the radiation energy incident on a surface that is absorbed by the surface. Okay, so if we have certain Q incident on the surface, you know that not most of the heat absorbed. Some of it, or a fraction of it, absorbed, and the other fraction will be reflected away. Okay, so in order to account for the amount of the Q incident absorbed, okay, we'll substitute alpha, which represent the amount that has been absorbed. And of course, we have an ideal surface, a black body. A black body absorbs the entire radiation incident on it, and alpha equal to 1 in the case of ideal surface, black body. So Q absorbed equal alpha multiplied by Q incident. If we have black body, then alpha will equal to 1. Okay. Now, Kirchhoff's law, we must apply this law before uh, see the general equation for radiation that represent the absorptivity and emissivity. Okay. Of course, I'll go back here a little bit. So this Q emitted, sometimes we call it E emitted. E from emitted, E dot. Okay. And Q absorbed, sometimes we call it G dot. Or we call it irradiation. Okay. The absorbed energy, we call it irradiation. So Kirchhoff's law says that the emissivity and the absorptivity of a surface at a given temperature and wavelength are equal. So usually epsilon and alpha, we are talking about same surface at a given or at same temperature and same wavelength. We'll assume it they are equal. So this is emissivity must equal the absorptivity. Net radiation, since we have Q emitted and we have Q absorbed or Q incident or irradiation. Okay, so we need to calculate the net radiation because at the same time this surface will absorb certain Q from surrounding, and at the same time it will emit certain Q from its surface. So we need to calculate net radiation. Net radiation heat transfer represents the difference between the rates of radiation emitted by the surface and the radiation absorbed. The determination of the net rate of heat transfer by radiation between two surfaces is a complicated matter, since it depends on the properties of the surfaces, their orientation, the interaction of the medium between the surface with the radiation. So, for example, here, this is the most important parameter affecting the net radiation. So, usually we did this experiment, but I'm not sure if you will do it in the lab. So, here you have source or emitter, and here we have receiver. Okay, here we have sink or receiver. So, this source will emit certain radiation. So the amount of radiation that this receiver absorbs depends on the distance between the two objects, okay, and depend on the orientation of the sink, whether it's completely faced the source or it's a little bit inclined, okay, or oriented to another direction. So the orientation is very important on determining the net radiation. The medium here between source and sink, okay, the interaction medium between them, the properties of the surface. If we have, remember the surfaces that we start with, our part, heat transfer part, uh, maybe I did not mention here. So if the surface, if we are talking about black body, then the amount of radiation will be 100. Okay, it will absorb most of the radiation. But if we have black body with uh, stainless steel, okay, so some of the radiation will be reflected. So the properties of the surface is very important in determining the amount of heat radiation absorbed or emitted. The radiation is usually significant relative to conduction or natural convection. So most of the time we'll ignore radiation because it happens in uh, very few uh, rates, but it is significant in the condition of conduction only or conduction and natural convection. Okay, but this radiation negligible when we have force convection. Okay, if we have force convection, then we ignore the amount of radiation. When a surface is completely enclosed by a much larger surface at temperature T surrounding, okay, so imagine that, and here also I'll compare T surrounding with T infinity, okay. So imagine that this flat body, okay, flat plate, whatever, a surface is completely enclosed by a much larger surface at temperature T surrounding, separated by a gas that does not intervene with radiation. The net rate of radiation heat transfer between these two surfaces is given by Q dot radiation equal to epsilon sigma multiplied by surface area multiplied by Ts to the power 4 minus Ts minus T surrounding to the power. So I did a little bit modification to tell you what happens. Okay, let me go back to the previous slides. So here is the equation that represents the amount of Q emitted. Okay, and we call it either Q emitted or E dot, which represent sigma multiplied by epsilon as ds to the power 4 surface temperature. Now, in the case of absorbed, Q absorbed or G dot, which is equal to alpha multiplied by Q incident. Now, Q incident is equal to sigma. This is was not here, okay, so I added multiplied by surface area multiplied by surrounding to the power 4. Okay, so alpha sigma as T surrounding to the power 4, and here is T surrounding. A very close surface to a very closed location with respect to the surface. Okay, now from the Kirchhoff's law, we said that emissivity and absorptivity are equal at the given temperature. So here, I need to calculate Q dot net radiation is equal to one of them, epsilon, sigma, multiplied by AS. Now we'll subtract Ts to the power 4, surface temperature, minus T surrounding to the power 4. Okay. Now one of you might ask me whether T infinity equal T surrounding. No. The answer is no. They are not equal. Okay. Because T surrounding is very close to the surface, but T infinity is far away from the surface. Okay. Now, sometimes we assume them equal. In the problem statement, if he came and tell you that they are equal, that's it. Assume them equal. Otherwise, they are not equal. Okay. The difference between them, T surrounding very close to the surface, T infinity far away from the surface. Or we can write Q dot radiation in this format, okay, which is equal to H radiation multiplied by surface area multiplied by T surface minus T surrounding. Here in this scenario, I can substitute T surface either Celsius or Kelvin. Okay, but here in the previous equation or in previous form, only we can substitute in Kelvin. Okay, so yeah, this is the difference between two equations. And also we need an expression for H radiation. So H radiation will equal to sigma multiplied by epsilon multiplied by summation of T surface and T surrounding multiplied by Ts to the power 2 plus T surrounding to the power 2. And here again we need to substitute Kelvin in each scenario. Okay, so Kelvin, only Kelvin. Now this form we can consider it as one form because if we need to apply this one, we need an expression for H radiation which comes from here, or we can apply this equation in order to calculate Q dot radiation. Now we said here that radiation is significant when we have conduction or natural convection. So when radiation and convection occur simultaneously, here I'll add natural, occur simultaneously between a surface and a gas, then Q dot total is equal to H combined multiplied by surface area multiplied by Ts minus T infinity. And here we assume that T infinity is equal to T surrounding. Now, the combined heat transfer coefficient H combined includes the effect of both convection and radiation. So, if I set that, this is the equation here now. Q dot total is equal to H combined as Ts minus infinity, then H combined is equal to summation of H convection plus H radiation. H convection determined experimentally as we mentioned earlier. Q radiation we have an expression for it. Okay, so we can substitute here. Or we can find the total heat transfer as the following: Q dot convection plus Q dot radiation. So we add each one separately from the other one without using H combine. Okay. And later on I'll talk about why we add Q together, why we have a summation. Okay. Thermal resistance concept. Okay. Usually you used to use thermal or electrical resistance instead of thermal resistance. So we'll use the same concept, okay, resistance, but now we'll add to it thermal. Okay. Now we'll visit again the previous equation, but now we'll talk about the thermal resistance concept in this equation. So let's start with the conduction heat transfer Fourier's law. So in this equation we said earlier that Q dot conduction is equal to K multiplied by A, area cross-sectional area, this is AC, multiplied by T1 minus T2 over L. Okay, or we can write minus here, and this one, instead of writing it like this, we can write delta T. Okay, so instead of writing the Fourier's equation like this, we can substitute instead of K multiplied by cross-sectional area divided by L by this parameter, which we call it R wall. So T1 minus T2 over R wall. This R, which is equal to L over KVA, okay, so the reciprocal of this expression, and its unit is degrees Celsius per watt. You can check why this is the unit, because K is equal to watt per meter Celsius or Kelvin, and here we have meter squared, and this is meter. So meter with meter cancel out, meter with meter again cancel out. We end up with watt 1 over watt over Celsius, or Celsius divided by watt. This W R wall we call it, or sorry, this R wall is called the conduction resistance of the wall. So this is R wall conduction. Okay. You can use R conduction as a direct subscript instead of wall. So we call it conduction resistance of the wall, or thermal resistance of the wall against heat conduction. The thermal resistance of a medium depends on the geometry and the thermal properties of the medium. So it depends on the geometry and the thermal property of the medium. So these two parameters, or three parameters, affecting the value of R wall. Now we have certain analogy between what you learned earlier or in the electrical course, the analogy between thermal and electrical resistance concept. So here is the normal thing that you learned in the electrical current flow in this direction. Okay, so here we have two junctions, V1, V2, or voltage difference. Here we have electrical resistance, and here is the flow of the current. It flows over the resistance. So the current is equal to V1 minus V2 voltage difference divided by the resistance. The resistance, its function is to resist the flow of the current. Here we'll have the same. Okay, we'll try to mimic what happens in electrical situation, and we'll apply the thermal situation. Here we have the resistance. Okay. Here in this slide we are talking about conduction resistance, and we have Q flowing over this resistance, certain type of heat transfer. In this scenario we have conduction. We have convection, then we'll have R convection. If we have Q radiation, we'll have R radiation, etc. Okay, and here we have two junction, 2 points at two different temperature. So T1 is higher, than T2. This is why we have the flow direction in this direction. Okay, and we said that from this equation that Q dot is equal to T1 minus T2 over R. So if you compare these two equations together, you will reach to a conclusion that in electrical, R electrical, we have R conduction as the same uh, in concept. Okay, I current, that is flow over the resistance. We have a Q in the thermal resistance, so they are related to each other. So the rate of heat transfer, we have electrical current in the electrical scenario. Thermal resistance, we have electrical resistance, and temperature difference, we have voltage difference. Okay, so this equation is completely identical to this one, and we can match between the terms that they have same meaning. Okay, so whatever we used here in electrical, it applies to thermal. For example, if we have resistance on series, then we'll have thermal resistance on series, more than one resistance. If we have, then R total is the summation of R. If we have resistance on parallel, then here we have resistance on parallel, and the R total is the same. 1 over R total is equal 1 over R for each resistance. Continue with the thermal resistance concept. Here we are talking about convection heat transfer, the Newton's law or cooling law. So in this equation we said that Q dot convection is equal to H multiplied by surface area Ts minus T infinity. Or instead we can write it in this format. Delta T, which mimic delta V, okay, and here we have Q, which mimic I, and here we have the resistance. In this scenario, if we have convection, then we have resistance for convection, and it's equal to 1 over H multiplied by surface area. So here we have 1 in the denominator, then the Q convection, R convection is equal to the reciprocal 1 over H multiplied by surface area. And again, it's unit the same. It will never change. The unit of the resistance. Why? Because H we have watt per meter squared degree Celsius, and here we have surface area meter squared. So meter squared cancel out, and we end up with degree Celsius over watt. This resistance we call it convection resistance of a surface. Now, when the convection heat transfer coefficient is very large, we are talking about very huge amount of H convection, then we have what? Do you remember the range of H? If we have natural convection, then we have lowest magnitude of H. If we have force, then the value of H become higher. If we have phase change, then we reach the maximum. Okay, so if we are talking about very huge amount of H, so this is very huge, then the R convection become very low. What's that mean? That means whenever we have forced or phase change convection, then the resistance is very low and the heat transfer will happen at very high rate. Okay, so H very high, R very low. As a result, Q dot convection is very high. So this is very beneficial parameter in order to refer to the amount of Q transfer. So if we have very weak resistance, even in electrical, if the amount of the resistance is very low, then the current will pass easily. So if the R is very low, then the Q can transfer easily. Okay, but if the resistance huge, okay, then Q convection will be resisted from this resistance. Okay. Now, when the convection heat transfer coefficient is very large, the convection resistance becomes 0 and Ts equal to T infinity. Okay, no resistance at all. So Ts will equal to T infinity. So take a look here. So if H is very huge, approach infinity, so we have here 1 over infinity. 1 over infinity means our convection is almost equal to 0. Then 0 multiplied by Q convection, this is 0. This side is equal to 0. And as a result, from here, Ts is equal to T infinity. Nothing will affect the heat transfer. And that means what? That is, the surface offers no resistance to the convection, and thus it does not slow down the heat transfer. This is the physical meaning. If I go back to the, let me erase this one first. If I go back to the previous relation here, for example, so if we are talking about very conductive material, conductive means it will transfer Q from one side to another side very fast. Okay, so if we are talking about conductive material, Q is very high. Then we are talking about resistance to be very low. Okay, so if you are very low, then Q will be very high. Okay, so conductive material, there is no resistance for heat transfer. Okay, so Q will be very high. If we are talking about Q very low, insulated material, okay, this is not conductive, then the resistance will be, so if K is very low, insulated material, then the resistance is very high, okay, and then Q amount of heat transfer for this insulation material, okay, will be very low. The same for other parameter, okay, for the same for the cross-section area. But if we have thick wall, so if we have very thin wall, what will happen? And if we have very thick wall, what will happen? Is it the same for Q transfer from one side to another? The answer is no. So if L is huge, then R very huge, okay, and then Q conducted will be very low through the thick wall, okay. But if we have very thin wall, L very low, okay, then the resistance is very low. As a result, if this is very low, then Q will be very high, okay. And you can notice this phenomena, especially in very old houses, okay. uh, I think أعتقد في بعض البيوت القديمة إذا بنحكي عن النابس القديمة مثلا، أو في القرى بيكون في عنا بيت للمخبرة أو شي زي هيك، بيكون جدران البيوت هذه very thick، وبتلاحظوا كثير كويس بالصيفية بتكون جوا البيوت هذه باردة جدا، اوكي، مع إنه الحرارة بالخارج بتكون عالية جدا. ليش؟ لأنه كل ما زاد الثيكنس كل ما زاد الريزيستنس، اوكي، كل ما زاد ال للجدران كل ما زاد الريزيستنس. نفس الإشي في البلد القديم في نابلس، وأهم حارة من حارات البلد القديم اللي هي حارة الياسمينة. حارة الياسمينة فيها الجدران very thick، okay. لو كنا بعز الصيف ورحت على هذه الحارة تشوفوا إنه الهواء جدا بارد. هذه الجدران جدا سميكة، بتشتغل على منع انتقال الحرارة أو تقليلها بدرجات عالية جدا. بس as engineer إذا بدنا نستعمل very thick wall في الكونستراكشن، إحنا قاعدين بنعمل التكلفة أضعاف. okay. So عشان هيك there is optimum thickness للجدران، وهذا مشروع اشتغلنا عليه إحنا والشباب، وإن شاء الله So هذا الفيزيكال meaning, this is the physical meaning of R convection or physical meaning of R conduction. Same thing for radiation. Okay, so here is the equation for radiation, or I said earlier we have another format of this equation: H rad multiplied by surface area multiplied by ds minus the surrounding, or I can write it in the final shape. Same scenario for conduction and convection. So R radiation will equal to, this is 1, so it's equal to 1 over H radiation multiplied by surface area, and H radiation has same unit of H conduction, which is what, per meter squared degree Celsius. Okay, so here we have meter squared, so meter squared cancel out, and we end up with Kelvin over watt or Celsius per watt. Okay, and we call it radiation resistance. Now, as I mentioned earlier, if we have radiation, that means we have natural convection. So they occur simultaneously. Okay, they occur simultaneously. So we said that Q, in order to calculate Q net, then we either use H combined or we add the Q together, Q convection plus Q radiation. And I said I'll tell you why we add these two Q together. Because Q represent or mimic the current. So if the current is separated here to I1 and I2, then we can say is that because you know there's two resistance on parallel, so the current will be separated. So the total current is equal to current 1 plus current 2. The same for the Q. Q will equal to Q1 plus Q2, or Q radiation plus Q convection. And this Q entering this medium when we have gas flow or liquid flow, okay, this Q entering this medium is equal to Q conduction. So here I can say that because we have two resistance on series, here I can continue by doing this. So this is R. Let me erase everything for you. So here we have resistance through the wall, so this is R conduction. And here we have two resistance on parallel. So if I find out the equivalent resistance, then it will be series, and here it will be series. Okay, so we have here Q flowing over it. So here Q conduction will equal to Q combined. Or we can say that here is the same equation. Q combined or Q conduction will equal to the summation of the other Q. Okay, because we have two resistance on parallel. So the radiation heat transfer coefficient, we saw this expression earlier. So either we'll benefit from Q dot magnitude if we have it, or we'll use this format, this expression. And if we are talking about H combined, then we must do this assumption: T surrounding almost equal to T infinity. Okay. So and H combined is the summation of two H's. Okay. Or we can say that R total. Okay. So R total is equal to, or 1 over R total is equal to 1 over R radiation plus 1 over R convection. Okay, so this represents R total. So R total, where we can substitute it. So here is the Q total is equal to H combined multiplied by surface area multiplied by T surface minus T infinity or T surrounding, because we assume they are the same. And here is equal to Ts minus T infinity divided by R, which are R total. So either we calculate Q total using this format, or we can calculate it using this format when we add H combined together, or we can find it using this format. So we have three scenarios. Okay, so either this format or this one. Okay, so as a summary, the thermal resistance for conduction is equal to this equation. Okay, L over K VA or T delta T over Q. The thermal resistance for convection is equal to 1 over H convection multiplied by A, and H R radiation is equal to 1 over H radiation multiplied by A. And all of these resistance, its unit is degrees Celsius per watt. So, composite wall. If we have composite wall, what's the meaning of composite wall? If we have more than one layer. So here we have layer A, and here we have layer B. Okay, so as you can see, this side is at higher temperature than TS1. T surface 1 is very large than TS3. Okay, here we have at the middle, at the interface, we have T2. Okay, so the heat or the Q will transfer in this direction. This is the direction of Q in one direction. So here in this side we have uh, fluid flowing, and this fluid is very hot. Okay, so this is why Q transfer from this flowing fluid to this surface. So T infinity 1 is the highest, and here we have TS1. Okay, and here we have cold fluid flowing. Okay, so T infinity 3 is much lower than the T surface. Now for layer A, we have thermal conductivity for layer A. It could be, for example, if we are talking about the walls in our buildings, then maybe this layer represent the, for example, rock, and this one represent the concrete, for example. Two different property, two different layers. Okay, so this is thermal conductivity A, and here this is the thickness of this layer. Here we have different thickness, and here we have different thermal conductivity. But both of them, both of layer A and B are uh, in the sequential arrangement. Okay. Now, how we can transform this problem into resistance network. So here we have resistance from the convection. This is resistance for convection. Here we have resistance for wall A, and here we have resistance for wall B, and here we have resistance for R convection up. So you can notice that all of them on series, or I can write it like this. So this R for convection 1, H1. So this is R convection 1. And here H3, then this is 1 over H3, so this is R convection 2. By the way, it must be says that here that this is H2, okay, but because here we name it 3, then I'll leave it as T3 and H3, okay. Now in between we have R conduction 1 or R conduction A plus R conduction B. And of course, once we start writing the resistance network, okay, we must keep in mind that each resistance will have a starting point and ending point or two junctions. So, for example, Q convection, it works between T infinity 1 and T surface 1. R conduction A is between two temperature T surface 1 and T2. R conduction for layer B is between two temperature T2 and T surface 3. R convection 3 between T surface 3 and T infinity 3. So if I wish to find R total, so this represents R equivalent or R total. So this R equivalent will works between T infinity 1 and T infinity 3. Another important notice, so here I'll substitute Q. So Q will pass over R convection 1. It is the same as the Q passing through the R conduction A, same as Q passing, same, it is the same or mimic the current, okay? So Q, the amount of Q will be the same, and same Q will pass through R convection 3. And it is the same that is passed through the R equivalent. So Q remains same for series resistance, okay? So the total thermal resistance in series is equal to R total, R conduction plus R convection. Okay, so if we need to consider only this R as R equivalent or R total, so we can add these two together, or we can add all of them together. Okay, so R total for all of them is equal to R convection 1, R conduction A, R conduction B, R convection 3. So R equivalent for all of them will be between two junctions, T infinity 1 minus T infinity 3 divided by R total. Okay. Another important notice that Q is similar on each one. So this is Q that we calculate from R total. We can go to first resistance R convection 1 and says that this Q is equal to T infinity 1, whereas here is Q R convection 1, which is between T surface 1 and T infinity 1. So we subtract them and equate it to the Q total, okay, divided by R convection 1. The same for R conduction 1, which is between T2 and TS1, okay, and we equate it again to Q, which calculated from here, okay. So these scenarios give us an opportunity to calculate any unknowns, okay. For example, if Q was unknown, okay, and for example T2 is unknown, okay, so we can easily go and another thing, T infinity 3 is known, T infinity 1 is known, and H known, everything else known, okay, so except Q is unknown and T2 is unknown. So we can go first calculate Q from this equation, and then we can go to T2 and find it from this equality. Okay. Next lecture, I'll start from here. So I'll stop up to this slide. Then next lecture, we'll start from here. And I think most of the theory we finished it. Okay. We only need to talk about the overall heat transfer coefficient. And then we'll start with the first problem. Okay, so I will delay this one up to the next lecture. Then we'll start solving problems. Then stay safe and see you.